begin. So let's see where we left off last time. We ended the class talking about what a critical point is, or a critical number. Is equals C of f of x is a number such that f prime of C is equal to 0, or f prime of C is undefined. So this was what we called a critical number. A critical point of f of x is a point C comma f of C with C as of. So that's a critical point. Should note informally. So it's kind of not correct to say this, but oftentimes you'll just say the x-coordinate is the critical point, right? So I might say x equals 3 is a critical point. It's not really the point, but it implies the point. So even though technically it's not a point, it kind of, informally we'll just say, okay, x equals 5 is a critical point. And you should know what that means is, if I plug x into the derivative of the function, it'll either be 0 or undefined. Now, these points we knew were important because ultimately we want to figure out where maximums and minimums occur. Fermat's theorem told us that a point like this is probably where we want to look, and examples like absolute value of x tells us that points like these are also where we want to look. And so we define such points to be very important, and we call them critical points, and the x-coordinate of such a point is called a critical number. There might be other issues here. Well, there's another scenario, because usually at the endpoints of a closed interval, you could have what we saw also. We saw examples like, okay, so here was A and here was B, and we had a max at B. And so sometimes it turns out that at points like that, the derivative just might not even be a thing that you can even talk about, because there is no other side, as well as it might not be able to talk about the slope being 0 there, but the endpoints can themselves be pretty important, because they might themselves be maximums or minimums in the absolute sense. And so to deal with issues like that, we have something called the closed interval method. So the closed interval method says f is continuous on AB. Then we can find absolute extrema. Remember, extrema was just another name for maximums and minimums. By 1. Finding all critical points. And evaluating the y values. 2. Evaluating the y values at the endpoints. And 3, comparing the values in 1 and 2. The largest is going to give you the absolute max, and the smallest is going to be the absolute min. Okay. So the critical points could potentially tell us where local maximums and minimums are, but we might not use that information to be able to evaluate the endpoints, so we evaluate those separately, and ultimately we look for the biggest guy overall, and that will be the absolute max. The smallest guy overall will be the absolute min. And you can notice by the extreme value theorem, we're guaranteed to have both in this scenario. If our function is continuous on a closed interval, we're guaranteed to find a absolute max and min. That was the extreme value theorem. So basically, by a combination of these two methods, which in practice, like on a test or a quiz, I'd only ever ask you to attack one at a time. But by a combination of these two methods, we can find all sorts of maximums and minimums. Usually, if we want to find the local guys, we look at points like this. Whereas if we want to find the absolute guys on some closed interval, we use what's called the closed interval method. Right? So it would depend on how a problem is phrased. So if I just ask you, oh, find the critical points or find the local maximums and minimums, you'll kind of look at these guys. And if I said, find the absolute max on some interval, you look at this guy. So that being said, I think all there is left to do now in this section are examples. So let's actually put this into practice and do some examples. At this point, I just want you to find the critical points. I'm not going to ask you to classify them yet. We'll deal with that later. Find the critical points of the following functions. Equals x. Equals absolute value x. Y equals x cubed. Y equals sine x. I gave you a restricted domain here. Again, with a restricted domain. So just identify the critical points of those guys. At a later point, we'll talk about classifying critical points, but I won't do that here. Meaning, once you find a critical point, how do you figure out, is it a maximum or a minimum or neither of these? Okay, so we'll talk about that later. Right now, I just want you to know how to actually find them, how to locate them. So, how do we find the critical point of this guy? What are its critical points? So for a critical point, what would you do?
Find the derivative.
Find the derivative, and what are you going to check?
When it's 0 and it's undefined.
Great, so for critical points, we're going to set y prime equals 0 or undefined. Now, y prime is, for that guy?
1.
1. Right? So now you'll realize this guy, never 0. It's always 1. It's also never undefined. Conclusions.
No critical points.
Y equals x has no critical points. Right? Just because they're a thing doesn't mean everyone has to have them, right? So here's an example of a function that has no critical points. Okay, let's look at B. Y equals absolute value x for critical points. Set y prime equals 0 or undefined. What does y prime look like here?
Plus or minus 1.
Plus or minus 1, specifically, positive 1 if your x is greater than or equal to 0, minus 1 if your x is less than 0. Now, individually, these guys are never 0 themselves, and they're never undefined. However, at the point x equals 0, it's undefined. This is undefined. So here we can see y prime not equal 0 for all x. But y prime is undefined for x equals 0. And so x equals 0 is a critical number. Now I could say a critical point, but technically the critical point would be 0, 0, right? C. Trying to make things a little bit more interesting. So I have y equals x cubed. I know for critical points, I'm going to set y prime equals 0 or undefined. Now y prime is equal to 3x squared. Right? So this means if I set 3x squared equal to 0, this means that x equals 0. So that's a critical number. Y prime never undefined. So that function has one critical point, namely at the origin. the derivative?
Cosine x.
Cosine. So here we're going to set cosine x equals 0 or undefined. And cosine x happens to never be undefined. It's continuous on the entire real line. So you can, of course, ignore this part. But where's cosine of x equal to 0?
Pi over 2 and 3 pi over 2.
That's on the interval 0 to 2 pi. By the way, in general, how do you say where cosine is 0? Like in general, how would you say that? When would be the next time it hits 0?
5 pi over 2.
5 pi over 2. Next time?
7 pi over 2.
No, notice a pattern?
Every multiple of pi over 2.
Not every multiple of pi over 2. Odd multiples of pi over 2. Right? 1, 3, 5, 7. Going the other way, -1, -2. Okay. So this is n pi over 2, where n is odd. Okay. Kind of something you should know. By the way, if sine of x equals 0, it means that your x is n pi, where n is any integer. So of any multiple of pi, the sine will hit 0. Any odd multiple of pi over 2, the cosine will hit 0. It's kind of something to know there. So here, the critical points of this guy, or critical numbers, is going to be those two in that interval. So if you ever wanted to find where the max and minimum of sine would happen, those are probably the 2 points you'd actually check. And for those of you who know what the graph of sine x looks like, yeah, we pinned it right on the nose. The maximum occurs here and the minimum occurs here. But we'll worry about that some other time. Right now, just locating the critical points. Let's look at E. Do you remember what the graph of tangent looks like? Or is it undefined? Tangent is sine over cosine. It's only undefined where cosine is 0. We know cosine is 0 at all odd multiples of pi over 2. So minus pi over 2, minus 3 pi over 2, etc. Pi over 2, 3 pi over 2, etc. The graph looks like this. Knowing that, right, so it's going to hit 0 when sine is 0. So this point here is actually minus pi, whereas this point here should actually be pi, obviously not drawn to scale. But looking at that picture, can you kind of guess where the critical points would show up? Where looks critical here? Well, it should be no surprise to you that on this interval, minus pi over 2 and pi over 2 should be critical points because the derivative definitely doesn't exist there, at least. Probably another guy, if you thought about x cubed, you might think here should give you a critical point, although it does look like a max or min. So at the very least, I would guess these 3 points, where 0 is kind of iffy. And let's actually just see. Y prime, what's the derivative of tangent? Secant squared. Which you might notice is 1 over cosine squared. That automatically tells you whenever cosine is 0, that guy's not going to behave. So for critical points, set y prime equals 0 or undefined. Now here, y prime is never 0. Right? Because you have a fraction where the numerator is 1. The only way a fraction can be 0 is if the numerator hits 0 and this one never hits 0. So the y prime is never 0, which means all critical points comes from where y prime is undefined. And we know on that interval, this means that our critical points are going to be minus pi over 2 and pi over 2. In general, it would be every odd multiple of pi over 2. But there will be no critical points otherwise. Look at this guy. You might not know what the graph of this looks like yet, although you should be able to give a naive sketch of that without too much trouble. You would have learned that in pre-calc. But let's not worry about that right now. We're going to learn to sketch things like that in a lot more detail than you did in pre-calc eventually. But let's actually look at that. Derivative here.
4x cubed minus 8x. 8x.
So no critical points. Y prime equals 0 or undefined. It's never undefined, it's a polynomial. So I'm going to set that equal to 0. Now we just have to solve that equation, which by now should be fine. Just factor out a common term. And that will give us x squared minus 2. So you get x equals 0, x equals radical 2, x equals minus radical 2. Those are your critical points. This one has 3 of them. Yeah.
For purposes like for showing work like on tests and quizzes, you also write critical points where the derivative of y is equal to 0 or undefined every time.
Yes. Yeah, and like I said, in general, how I tend to write things down on the board is kind of how I expect you to write it. The reason being is that it's very common for students to forget about checking the undefined situation, and there are some times where that's the only case where the critical points show up. For example, here. If you forgot to check here, you might have concluded, oh, there are no critical points, but you'd be wrong. So yeah, I like when students write this sentence as a reminder that there are 2 things you need to check. Right? People usually remember setting the derivative equal to 0 because they imagine the picture of the horizontal tangent line, but there's more cases to worry about than that. Y plus square root of x. Here, your y prime is going to be 1 over 2 radical x. And for critical points, y prime equals 0 or undefined. In this case, it's never 0. And we know y prime is undefined at x equals 0. That means x equals 0 is I don't know where to put that in right. That's the answer. Okay, so we know how to find critical points. So usually if we're searching for maximums and minimums, which is going to be an important endeavor in many scenarios, these are kind of some of the places we'd look first. Let's give you another kind of example. So on a quiz, I might ask you a problem like this, find the critical points. On a test, you probably won't see a problem like this, because usually by the time the next test comes, we'll have gone so far where finding a critical point is just going to be one step in a multi-step problem. Right? So by the time the test comes, you're not going to have a standalone problem asking you to find critical points. But the next quiz might. But usually if we're finding a critical points, it's to use them to do something else. So this example here is kind of like a quiz problem, but not really a test problem, if you want to phrase it that way. A test problem will be like this, though. Usually there will be like a standalone problem that asks you something like this. So, last example, this problem, not test problem. This next example is both quiz and test. So in terms of what to expect. So you'll see a problem looks very similar to this. It's going to again be phrased very similar as well. So it's going to say something like, find the absolute extrema of f of x on a given interval. Okay. Now, of course, there are some synonyms that we know about that might be substituted here. So instead of the word absolute, you might see the word global. Instead of extrema, you might see them spell out maximums and minimums. But it should be clear to you in either case what they're being asked about. I pretty much never use the word global. I don't think a lot of people use it. I'll pretty much always use the absolute. So you might see a problem like this. Find the absolute extrema of this function. And every time they ask you about an absolute extrema, they will have to give you an interval. Because of the extreme value theorem, you're really only guaranteed to have these things on a closed interval. So that might be a follow-up question. How do you know this exists? And your answer would be something like, well, the function is continuous and we're on a closed interval. So the extreme value theorem tells us it will exist. Okay, so let's actually do a few of these guys. And basically, whenever you see a problem like this, you're going to use, I'm not going to tell you this on a test or on a quiz, but you should know. You're going to use the closed interval method. So see your problem, say, find the absolute extrema of this function on this interval. You should know, oh, closed interval is a method. You should also know, I'm guaranteed to be able to find these if the function is continuous, and you'll usually see a function is continuous. So if there happens to be, I don't know if I do it, but if there happens to be a follow-up question, something like, how do you know that they're even there? You'd say something, oh, the extreme value is continuous instead of closed interval. I only wrote down 2 examples here. Anyway, here's one. I hope I chose that interval correctly. thought I wrote down more examples, but I guess we'll only do 2. I think these should illustrate everything I want to illustrate of what could happen here. You know what, not quite. Trying to think of what evil tricks I would put on a test. Making this a 1 would be nicer. Okay, let's do that. So we have y equals x to the 4th minus 4x squared on minus 1, 3. So step 1, we're going to find the critical points. So we'll kind of end up where we did last time. This is going to mean the 4x squared minus 2 equals 0. So you end up with x equals 0, x equals radical 2, x equals minus radical 2. So now, here's where the trick would come in. Not all of those are valid options. Can you see why? Negative radical 2 is not in that interval. Okay? So you can have something. So here you'd reject. Not in interval. So it's possible for a problem to kind of trick you. You have to pay attention to where you should be looking. Right? This guy's outside that interval. Right? Radical 2 is 1.4-ish. So it's definitely, negative radical 2 is definitely over here. So that's the first thing. So now, remember step 1 is to find the critical points and evaluate them. So what we're going to do now is we're going to find y of 0. And y of 0 is going to be 0. We're then going to find y of radical 2. Right? Now to find y of radical 2, I'm going to plug in radical 2 here. Radical 2 squared is 2. Square that again, you get 4. Radical 2 squared is 2. Multiply by 4, you get 8. 2 gives you minus 4. And those are the only 2 critical points. Now, do step 2. You worry about the endpoints. Now the endpoints are just given. Similarly, you're just going to plug those in. I'm going to find y of minus 1, and I'm going to find y of 3. So if I plug in minus 1, I will get 1, minus, plug in minus 1, I will get 4. That gives me minus 3. If I plug in 3, that's kind of 4 times 9. What's that going to be? 3 to the 4th is what? Times 9?
6.
Huh?
36.
6. And 81 minus 36. 45. So now that brings us to step 3. We're going to compare. So basically, in steps 1 and 2, I found a bunch of y values. All I'm going to do now is go through those and pick out the largest and the smallest ones. Okay? So I have 0, -4, -3, and 45. 45 is obviously the largest one. So the absolute maximum here happens at the end point. It happens at 3. So I'd be able to say absolute max is y of 3 equals 45. And I'll be able to say absolute min. It's customary to actually express it this way, to both express what the x value is and what the output is. And the absolute minimum will be the smallest one. That happens at one of the critical points, that's -4. So it's y of radical 2 equals -4. And that's my answer. Okay. So at the moment I don't know what this graph looks like, but I do know that if I plotted it on this interval, the largest point is going to be at the right endpoint. It'll have a value of 45, and the smallest point will be located at radical 2 with a value of -4. Right. And the fact that that doesn't happen at the endpoint means something, but like I said, we'll talk about that later. Any questions on this? So this is how you apply the closed interval method. Just go through those 3 steps. Find the critical points, evaluate it, evaluate at the endpoints, then you compare everyone. The largest guy is the absolute max, the smallest guy is the absolute min. Good. Okay, so 1, let's find the critical points. So f prime is going to be, what's the derivative here? Why is everyone just always making Julie answer? It's not fair. And how do you differentiate that?
Is it negative sine, or -2 sine x?
-2 sine x? No.
Like that.
It's cosine of
Negative,
2x.
yeah.
2x is the inside function.
It's negative sine 2x times 2
Right,
which
which makes
yeah.
this plus
plus
2
2
sine
sine
2x.
2x. Yeah, that's what I was
So that's the derivative. Okay, so chain rule. And so now I want to set f prime equals 0 or undefined. This is a sum of 2 continuous functions, so it's never undefined. So this means I need 2 cosine x plus 2 sine 2x equals 0. How do I do that? Well, sure, I can divide both sides by 2, but after that, how do I solve that equation?
Sin 2x is an identity, right?
We do have an identity for it, yeah. What is it? Sine 2x. Another way to write that is to express it in maybe where the angle is x. Right, let's double angle formula. So you have cosine x plus 2 sine x cosine x. How do you solve that?
Plot of cosine?
Huh?
Plot of cosine?
Plot of cosine, you can factor this. So cosine x times 1 plus 2 sine x equals 0. What does that mean?
Then you can just separate them, so.
Right, so that means cosine x is 0, or it would mean that your sine x is minus 1/2. Okay, so cosine x equals 0, we should know that by heart. That is going to be on 0 to 2 pi, that's going to be pi over 2 and 3 pi over 2. So those are points we have to check. Where is sine equals minus 1/2? Maybe preliminary question, where is sine equal positive 1/2?
Over 6.
Or pi over 6. Right?
So it's negative 1/2 at 7
So-
pi over 6.
And here's the circle of the quadrants. We know pi over 6 is where it's positive 1/2. And these are the other reference angles. And we remember that all students take crap. So for the sign to be negative, we need to be down here. Right? And we know pi over 6 means you divide pi into 6 pieces. And so this will be 6 pi over 6, 7 pi over 6. And 6, 7, 8, 9, 10, 11 pi over 6. So those are the 4 points. By the way, I don't remember if I told you guys how to memorize the special angles, but the easiest way is to do it via a table. So you can put the theta over there, sine theta, cosine theta, set up like that. You go up with the special angles, 30, 45, and 60 degrees, which you should know that's pi over 6, this is pi over 4, this is pi over 3. In the sine row, count up from 1 to 3, 1, 2, 3. Cosine row, go backwards. Take the square root of everybody, and then divide everyone by 2. So that helps you. I think it's nice to do it in a table because it helps you to also use positional reasoning in your memory. So you're, okay, sine is 1/2, well that's the top left corner, that's where the pi over 6 is. And you can know that sine of 1/2 is, sine of pi over 6 is 1/2. And sine of pi over 4 is equal to 2 over 2. Cosine of pi over 3 is 1/2. Cosine of pi over 6 is equal to 3 over 2, etc. Right? Once you figure that out, that tells you how here behaves. And then you can just slice up the circle and count off wherever you want the reference angles to be. But ultimately, we would get these 4 things that we want to test. And they're all in 0 to 2 pi. So here, you go f of pi over 2. This is 2 sine pi over 2 minus cosine pi. Sine of pi over 2 is 1, cosine of pi is negative 1. And f of 3 pi over 2, 2 sine 3 pi over 2 minus cosine of 2 pi over 3. Because I multiplied by 2. So sine of 3 pi over 2 is minus 1. Cosine of 3 pi is also minus 1. And f of 7 pi over 6 will be 2 sine of 7 pi over 6 minus cosine, multiplying that by 2 will give me 7 pi over 3. Sine of 7 pi over 6, we already have the circle for that. 7 pi over 6 is here. That means the sign is the negative value. It will give you negative a half. To figure out the 7 pi over 3, when you draw the circle, that's 0 and pi divided into 3 sections. So each section is pi over 3. And again, all students take crack. And 7 pi over 3 would be 1, 2, 3, 4, 5, 6, 7. 7 pi over 3 is actually in the first quadrant. Too much multivariable. And so it'll give me the same value as the cosine of pi over 3 over there, which is also a half. Okay. So it's minus 3 times. Okay, now I remember why there was 2 examples. I expected things to slow down in the trig part. Okay, what else do we have? One more, right? So here we now have f of 11 pi over 6. That's going to be 2 times sine of 11 pi over 6. 11 pi over 6 shows up here, because the full circle would be 12 pi over 6. And so that's also going to give me a minus a half. Minus cosine of 11 pi over 3. A full circle is 6 pi over 3. And so 11 pi over 3 is going to end up here. That's going to be 11 pi over 3. Because you know 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the cosine is actually positive in that case. And we know at pi over 3, by memorizing that table, it's a half. So I get here instead of here. Two, test the endpoints. F of 0. Well, sine of 0 is going to be 0. Cosine of 0 is 1, so that's just minus 1. F of 2 pi. Sine of 2 pi is 0. And if I plug in 2 pi here, I get cosine of 4 pi. Cosine is positive 1 at all even multiples of pi. And so that's minus 1. Which brings us to step 3. Who's the biggest? Who's the smallest?
Pi over 2 is the biggest.
Pi over 2 gave us 3. So I'd say absolute max is f of pi over 2 equals 3. Who's the smallest?
7 pi over 6 and 11 pi over 6.
Right, those both give us the same answer. So we'd say absolute min is f of 7 pi over 6 equals 11 pi
over 6 f of 11 pi over 6 equals minus 32.
And ultimately that would be the answer. And we're out of time. So we'll stop there. You have a quiz later on what we did last week. And on Friday we'll actually talk about the mean value theorem in real estate. So that's just a look ahead.